This training is part 1 of mid-level system design and analysis. It will explain NPSH, total dynamic head, friction losses, and will cover an example problem calculating the total dynamic head of a system. NPSH, or net positive suction head, is the term used to describe the margin of pressure over the vapor pressure of the fluid at the pump suction. The units for NPSH is feet of head, and it has two components, NPSH required and NPSH available. For the pump to function properly, NPSH-A needs to be greater than NPSH-R. As long as the NPSH-A is greater than NPSH-R, the pump will prime and avoid damaging cavitation. Both terms are covered in depth in the following slides. NPSH-R is defined as the suction pressure at which a pump's pressure output is degraded by 3%. The image to the right illustrates what happens to the pressure of the fluid at the eye of the impeller. Pump systems need to maintain a positive suction pressure that can overcome the drop in pressure to avoid crossing the vapor pressure line. If the pressure does drop below the vapor pressure line, vapor bubbles start to form at the eye of the impeller. As the bubbles move from the eye of the impeller to the outer edge, the pressure increases and causes the bubbles to collapse or implode. This is the definition of cavitation. A deeper look into cavitation will be covered in a later slide. NPSH-R is dynamic and changes as the flow changes. The greater the flow, the greater the NPSH-R. It is determined through testing, and the pump manufacturer should provide values at given flow rates on their standard pump curves. The next slide will cover the testing procedure in more detail. When testing a pump, all variations of a hydraulic performance are considered, including head, flow, and power. Cavitation is detected on paper as a drop in head at a given flow rate. While cavitation can exist without head degradation, NPSH-R is defined as a 3% reduction in discharge head. 3% is a Hydraulic Institute standard. The pump is initially run at a given head and flow, and the discharge pressure or discharge head is recorded. The pump is then subject to an increase in suction lift, reducing NPSH-A by a specified amount, then the discharge pressure is measured again. These points are plotted on a graph as shown. This process continues until we see a 3% reduction in the discharge pressure. While NPSH-R is a known performance characteristic of a given pump and is provided by the pump manufacturer, NPSH-A varies depending on what the suction side of the pump looks like. NPSH-A is the pressure available in the system on the suction side. It is a function of the local atmospheric pressure or elevation, the static suction lift, friction losses in the piping, and the temperature of the fluid. It may help to think of NPSH-A like a bank account, and the calculations are like balancing your budget. Atmospheric head is your monthly paycheck, and static lift, pipe losses, and fluid temperature are your utilities and expenses due each month. NPSH-R is your fixed food bill for that month. You start out the month with your entire paycheck in the bank. After all your utilities are paid off, you need to make sure you have enough left to buy your food. If you have more money available for food than was required for other bills, then you are able to eat. Subsequently, if NPSH-A is less than NPSH-R, the pump will cavitate. The image shows the maximum amount of money one can have in their bank account. At sea level, the atmospheric pressure is 14.7 psi, which equates to 34 feet of head. Every 1,000 feet in elevation gain, you lose about 0.5 psi in atmospheric pressure. Cavitation occurs when the pressure at the eye of the impeller drops below the vapor pressure of the liquid. When water turns to vapor, its volume increases drastically and limits the amount of water that can be moved through the casing. The collapsing vapor bubbles are extremely powerful and will eventually erode and damage the impeller, as the images show, and other components inside the blue case. Cavitation also usually leads to excessive vibration, which can cause premature failure of bearings and seals. An easy indicator of cavitation is when the pump casing, during operation, sounds like it's full of small rocks. To get a full understanding of just how much elevation can affect NPSH and static suction lift, let's compare max static lift in Los Angeles, which is very close to sea level, with max static lift in Denver, which is 5,300 feet above sea level. At sea level, the pump sees 34 feet of atmospheric head. Both sites are using the same pump, and the NPSH-R is 13 feet. Vapor pressure head is 1.5 feet, friction losses in the piping are 4.5 feet, and the NPSH safety margin is always 2 feet. The maximum static suction lift for this pump is 13 feet. Now for the pump in Denver. At 1 mile high, the pump only sees about 28 feet of atmospheric head. NPSHR is still 13 feet. Vapor pressure and friction losses are the same at 1.5 and 4.5 feet respectively. The NPSH safety margin is 2 feet, leaving the maximum static suction lift at only 7 feet. The conclusion here is that pumps cannot pull as much static lift at higher elevations. Switching gears, total dynamic head is defined as the sum of static head and dynamic friction losses in the system on both the suction and discharge side. Summing both sides becomes easier if the suction and discharge sides are analyzed separately. Be sure to note the static head and desired flow rate for the application. A simple way to calculate friction losses is using what is known as the equivalent length method. The next step is to convert all the fittings to their equivalent lengths of straight pipe. Those equivalent lengths and the actual total lengths of pipe are added together and used to find the total friction losses. Static head and total friction losses are added together to get total dynamic head. Let's now work through an example in calculating total dynamic head of a simple suction lift application. The pump is a 4-inch self-primer with a flow rate of 300 gallons per minute. All pipes and fittings are standard 4-inch ductile iron and will be analyzed using the equivalent length method. Calculating friction losses can be done in several ways using several different methods, but the two most popular methods are the Darcy-Weisbach and Hazen-Williams equations. The Darcy-Weisbach method is most commonly used to calculate pipe friction and is used to create the friction charts in the Cameron Hydraulic Handbook. Hazen-Williams is also used to calculate pipe friction, but is geared more to applications where the liquid is strictly clear water. This analysis will be using the Hazen-Williams formulas. Let's start with the suction side of the pump. The static suction lift is 10 feet, and the total length of straight pipe is 15 feet plus the 3 feet right before the suction flange, totaling 18 feet. The 90-degree elbow now needs to be converted into an equivalent length of straight pipe. The table shown has values tabulated for various sizes and types of elbows. The highlighted value of 10.2 feet is for a standard radius 90-degree 4-inch elbow. By adding the total length of straight pipe and the equivalent length of the elbow, we get the total equivalent length of suction pipe, which equals 28.2 feet. Static lift is added on top of friction losses, so it is not included in our friction calculations. Now that the total equivalent suction pipe length has been calculated, the next step is to find the pipe friction factor, usually expressed in the head loss per 100 feet of pipe. The friction factor for 4-inch pipe and a flow rate of 300 gallons per minute is 9.3 feet per 100 feet of pipe as shown in the table. 9.3 feet divided by 100 feet gives us 0.093 feet, the feet of head lost per foot of pipe. When we multiply the total equivalent length of pipe by 0.093, we get 2.6 feet. The total dynamic suction head is the static lift of 10 feet plus the friction loss of 2.6 feet, totaling 12.6 feet. The second half of this problem is analyzing the discharge side. The static lift is 23 feet and the total straight length of pipe is 9 feet plus 12 feet plus 150 feet. Just like on the suction, the fittings now need to be converted into an equivalent length of pipe. The fittings include one swing check valve, one gate valve, and two 45-degree elbows. According to the tables provided, the check valve is equivalent to 26 feet, the gate valve is 2.1 feet, and the two elbows total an equivalent 9.4 feet of straight pipe. The total equivalent length of pipe on the discharge is 208.5 feet. Just like before, the friction factor is 9.3 feet of head lost per 100 feet of pipe. To get head lost per foot, 9.3 feet is divided by 100 to get 0.093 feet. When we multiply 0.093 by the total equivalent length of 208.5, we get 19.4 feet of friction head loss. Total dynamic discharge head is the static lift of 23 feet plus the friction loss of 19.4 feet, totaling 42.4 feet. Remember, total dynamic head is the dynamic suction head and the dynamic discharge head added together. For this example, the total dynamic suction head was 12.6 feet and the total dynamic discharge head was 42.4 feet. These two added together equals 55 feet. The official total dynamic head of the system is 55 feet at 300 gallons per minute. The image shown is a typical pump curve describing how a pump will perform at various speeds and pressures. The positive sloping curve represents the system curve. This curve is created by calculating the total dynamic head at various flow rates and plotting those points on the graph to create a curve. This makes sense because as the speed or flow is increased, friction losses are increased, which causes total head to go up. In a given system, the pump will operate where the system curve intersects the pump curve. To use this curve as an example, when the pump is running at 1927 RPM, flow will be 1,500 gallons per minute, and the total head will be about 140 feet. This concludes Mid-Level System Design Part 1. We covered NPSH, which stands for Net Positive Suction Head. NPSH is split into two categories, NPSH Required and NPSH Available. Remember that NPSH-A is like a bank account, and atmospheric head is the monthly paycheck. Atmospheric pressure is not the same everywhere, so knowing the elevation at the pump site is important. We then discussed total dynamic head, what it means, and how we calculate it. And then finally we worked through a system design problem and calculated the total dynamic head using the equivalent length method. Be sure to come back for Mid-Level System Design Part 2, where we will cover pumping in parallel, series pumping, efficiency, the affinity laws, the effects of specific gravity and viscosity, and finally pump curves and selection.